So in the previous lesson, we talked about significant digits as it applies to addition and subtraction and how you do that. Okay, that we line up all of our digits vertically, lining up, centering on that decimal place, and any digits to the right that are added together resulting from any empty slot in that column, the resulting digit in the answer then is insignificant. It gets underlined and you round that off. Okay, you have to show all that in with the notation that you've been taught. Well, the same notation for rounding off applies here too. The only difference is how we handle the significant digits. And since most of the multiplication and division that we do in chemistry class, and in fact most science classes, will involve the multiplication of fractions, which means you're both multiplying and dividing all as one sort of operation, that's what I'm going to teach you. It's kind of short-circuiting some of the stuff about multiplication and division rules, but it's what we use in here, and if you learn to use it in here, you can use it in other contexts as well. So let's say that we're going, and in fact, if you saw your email last night, and I sent home some notes, and I think in fourth period, that's the class I recorded, and I may have gotten a little bit further. Did I get to a little bit of multiplication and division with you guys yesterday? Okay, so you probably already saw one problem on that if you looked at the notes. So what I try to do, and I can't promise I'll do it every day, but I try to scan these notes that I show you, and then I email them home to you. And some days I don't get to it. I might be just too busy to get to it. But if I can go next door and use the copier over there to scan it, I can forward it to you, and you'll have it. So you'll see this strange-looking email with some strange-looking subject line, but that's where the notes are sometimes, okay? All right. So let's start with a word problem like this. Let's say we've got 1 liter of nitrogen gas. Has a mass of 1.34 grams. Okay. Now I'm simplifying this a little bit because this relationship only applies if the temperature is, I believe it's 0 degrees C and the pressure is 1 atmosphere. Gases change their volume with changes in pressure a lot, very easily. Yep, 0 degrees C and 1 atmosphere. But I'm not going to put that down in this problem. I just want you to know ahead of time that's what it is. And by the way, 0 degrees centigrade, and you don't need to write this down. You'll see it again when we get to gas laws. 0 degrees centigrade, 1 atmosphere, that's called standard temperature and pressure. Okay, but you'll see it again. So what this means then is that a liter of nitrogen gas is equal to 1.34 grams of nitrogen gas, as long as we're at that right temperature and pressure. And so what we can do is write an equality statement that results from that concept. 1 liter of nitrogen, N is the symbol for nitrogen, equals 1.34 grams of nitrogen. Okay? And to solve these kinds of problems in this class, I expect you to always write an equality statement. If the problem implies an equality statement, I want you to write it out. There are going to be problems where you have to calculate the equality statement, and we'll talk about that when we get to that. Don't sweat that too much, okay? But right now, if the problem says something like this, where you have a liter of nitrogen gas that has a mass of this, that means they're equal, okay? So that amount of nitrogen gas, that number of moles of nitrogen gas, is equal to this volume and this mass. So they're actually equal, okay? And what that's going to do is allow us to build a conversion unit. And we're going to handle conversion units a little bit differently than they may be used to, because I want you to understand where conversion units come from. And so what we're going to be doing is building conversion units, not just writing them, building conversion units based on the concept of where they actually come from. And this will give you a deeper understanding of conversion units, which you'll be able to translate into other classes you take. So then the question is, how many liters of nitrogen are there in 3.97 grams? Now eventually you'll kind of figure out how this works without having to think it through. But our sort of training wheels start for this is you take your starting amount, which is this amount right here. The problem doesn't say this is equal to anything, so it kind of stands alone, and that's a starting amount. We're going to take our starting amount and put it over 1. Okay, so what we're going to do is say 3.97 grams. And as I've said before, if we know what a measurement applies to, you have to also say what that thing it is that it applies to. In this case, it applies to nitrogen. Okay, and a little terminology here. This is our unit of measurement, and this is our species. Okay, in chemistry there are species, even though there aren't any animals or plants. There are species. Okay, that's our chemical species, and we're going to put it over the number 1. Now that number 1 doesn't change the value. It's kind of a placeholder. It's a counting number. So when we're figuring out significant digits, this one doesn't matter. Okay, it's just there to make the math sort of work out for us a lot nicer and neater. Okay, and neatness does count in a lot of math, because if you get really sloppy, you can't tell what the math operation should be. So we're going to multiply it by a conversion unit, and we're going to build that conversion unit from this equality statement. And the way you do that is really simple. You match units and species. Okay, so here's the separator bar, or whatever that's called in math. Forgive me for not knowing what that is. You can ask your math teacher and tell me. Okay, but we're going to take the side of the equality statement with the matching units and species to our starting amount, and we're going to put that part on the bottom. Okay, everybody get that? Match the units and species with what's on the top here and put it on the bottom here. Okay? And then the other side of the equality statement will go on the top. So we'll put 1 liter of nitrogen, put it on the top. Okay? Pretty simple, right? Doesn't sound like it's all that complex, and it isn't. But if you'll do this every time, your life and all this math we're going to do in here and these really long stoichiometry problems we'll do later in the semester, it's going to be a breeze. Okay? Once you get used to this idea. And so what this allows us to do is we can cancel grams and the symbol nitrogen. It's just like x's and y's in algebra. If you have one on the top of a fraction, one on the bottom of a fraction, you can cancel them out. Yes? As long as you're not adding things, as long as you're multiplying in both places. Multiplication is the inverse of division. So this is multiplication going to the right and division going up and down. One undoes the other, and you can cancel out grams, you can cancel out nitrogen. Does that make sense? Anybody confused so far? Everybody's good? Okay. Would anybody admit to it if they were confused? You should. There's nothing wrong with being confused. Okay. In science, you've got to recognize your ignorance. There's a really interesting article. I think I put it on the outside of that door back there. You can read it sometime when you're going down the hallway about how important it is to be ignorant in science. Not so much being ignorant, but knowing when you're ignorant. Okay. If you don't know you're ignorant, that's a problem. And you need to know when you're ignorant to say so. Okay, just ask the question. Like, I didn't know what the name of this bar is here. Okay, I'm not afraid to tell you. I want you to tell me. If you can find out from your math teacher what the name of that bar is, tell me. Okay, I probably knew it one time. I just don't remember now. Good enough? Okay, so I'm trying to show you the way that you ought to think and approach things, and think like a scientist, as I'm trying to demonstrate that to you. Okay, one of the most important things that we as science teachers should be doing is helping you to think like a scientist. Okay, not that you're going to be a scientist necessarily, but when you think like a scientist, you understand how science works. Okay, all right. So we do the math, and if you've got a calculator, you're welcome to do any of these calculations on your calculator. Okay, I don't make you do anything in your head. You can use a calculator. All right, and the more you practice doing this, the more you repeat doing this in your calculator, the more you repeat doing this on paper, the more you're likely to learn. You probably have heard about learning styles. People talk about learning styles sometimes. You know, you might be a visual learner. You might be a kinetic learner, right? Yes? You don't know about those? Yes? Okay. Well, there's a misunderstanding about learning styles. Okay, the research shows that everybody learns equally well in all 3 domains of learning styles, and that's kind of a misunderstanding. Somehow over the years we've got this idea that people learn best with one kind of learning style over the other. It's not best. It's a preference. Okay, so you should use all the learning styles. Okay, visual, learning, auditory, all those are learning styles that will benefit everybody. But you may be more comfortable in one of those domains or another. Well, writing, guys, is a kinetic learning style. Okay, if you write things down, you're learning it by moving your hands. That's kinetics. That's moving things around. Okay, that's using your body to learn. Okay, so writing things down is a learning style. You should try to learn things by writing it repeatedly. That's why when you want to memorize something, you can write it over and over and over, and you can memorize it. That's why it works. Okay. All right. So the answer here, if you put it in your calculator, 2.962686567. Now your calculator may have a few more digits or a few less digits. That's okay. You're going to put down all the digits you have in your calculator. Okay? You want to try it out and see if you get the same number as me. That's good. Now what we've done is we've canceled all the units and species except for liters and nitrogen here. Okay? So that's what we're going to put on this answer because that's what it is. Okay? So what we found is that this number of grams of nitrogen is equal to this number of liters of nitrogen. The problem is this number only had 3 digits and this one only had 3 digits. How can we have this, whatever that is, 10 digit long number? That doesn't make sense really when you think about it. That's too many digits. Those digits are really, not all those digits are significant. And with multiplication and division, what you're going to do is you're going to look at your measured or calculated numbers in the problem. Look at all the measured or calculated numbers in the problem. And the measured or calculated number with the least digits is going to tell you how many digits to keep in your answer. So you're going to look at all of your measured or calculated numbers in the problem. And the measured or calculated number with the least digits is the one that's going to tell you how many digits to keep in your final answer. And so this is a measured number. This is probably a calculated number. And if it's got a decimal place in it, it's got to be either measured or calculated, almost always. Not always, I shouldn't say it every single time, but almost always. It's a really good clue. If there's a decimal place there, it's got to be measured or calculated, okay? So this is measured, this is calculated. Both those have 3 digits, so the least digits is both of those. It's 3 digits. And we're going to, just like we did yesterday, we're going to underline all the insignificant digits. If these are the significant digits, then all of these are the insignificant digits. And we're going to underline all the insignificant digits. And then we use that same operator, an arrow, to show we're rounding off. And our final answer is 2.96 liters of nitrogen. We're going to put a box around it to show that's our final answer. Yes?
Instead of a 2 right behind the 6, if you had...
So there are 12.01 grams of carbon in 1 mole of carbon. And the question is, how many grams are there in 0.473 moles? So solve this using the same process I outlined for you already. Let's see how you do. Okay, so our starting amount then is the 0.473 moles. Now, not every problem is going to be worded in this fashion, so you have to be able to interpret the problem. Okay, sometimes the problem will start with the starting amount. You have to figure it out. Okay, it's a matter of interpreting the information you're reading. So but this is the starting amount in this case. We've got 0.473 moles, and by the way, that's the shorthand for moles. I know that's kind of a strange shorthand, but if you were in Germany, that's the way you'd spell mole anyway. Moles of carbon, and the symbol for carbon is a C. Going to put the starting amount over 1. Going to multiply by a conversion unit, so we need an equality statement for a conversion unit. We're going to show that there's 12.01 grams of carbon. That's equal to 1 mole of carbon. And this 1 right here is a counting number. Okay, I didn't state that earlier when I showed you this one. But this is a counting number, so that doesn't apply to figuring out significant digits as well. This one is calculated. This one's measured. Actually, that you can't measure moles directly. You have to calculate it anyway. So both these actually are calculated numbers, but that's okay. They both have decimal places, so you should be able to figure out pretty quickly if those are either measured or calculated. And what we want to do is to match the units here on the top of this fraction with what I'm going to put on the bottom here. And this is the side of the equality statement that matches those units, so that goes on the bottom. And I'll put this side on the top. And if I've set it up correctly, everything should cancel but the units that I'm looking for, whatever measurement unit I'm looking for in the final answer. And I'm looking for grams, and so I've got grams on the top. That should work out. And so moles are going to cancel, and carbon's going to cancel. And I do the math, 5.68073. And there's probably some math teacher wincing right now and saying, no, it's not O, it's a 0. And they're right. And so this number has 4 significant digits. This one has 3 significant digits. Now, we haven't talked about significant zeros yet, so don't sweat it if you didn't quite get it right. Leading zeros are not significant. Don't worry about it. We'll get to that. And so I want to underline all but the first three digits. Those are the significant digits. Okay, and then 5.68 is the rounded answer, grams of carbon, and I'm going to draw a box around it. Okay, you might have listed 5.681 thinking that was 4 significant digits. Don't worry about that right now. Okay, if you got everything else right, you're good. Everybody clear? All right. Does that seem hard? Shouldn't be. And later on in the semester, you're going to be doing these problems that will take up 1 or 2 pages of work to do one problem. Okay? And it'll be all based on this right here. And if you just keep doing that over and over again, you're going to be good. Okay? You're going to be surprised at what you'll be able to do. Okay? Trust me. This process of canceling out units and species has a name, and it's called dimensional analysis. So moles is a dimension of measurement. Grams is also a dimension of measurement. So we're using dimensional analysis. We're canceling out those dimensions to get to the one we're looking for. Okay. Now here's our equality statement. Okay. So we have the units of measurement here, the units of measurement here. We want to match the units top and bottom here so that those units of measurement can cancel in this dimensional analysis process. Okay. Any questions about that? Here. Okay. So when we do a problem like this, and we have a defined relationship, like 1,000 grams equals 1 kilogram, not a calculated relationship, not a measured relationship, but a defined relationship, 1,000 grams equals 1 kilogram, or 1 liter equals 1,000 milliliters, that's defined. Okay, that's part of that metric system stuff. Okay, that King Henry, whatever that thing is you guys use, okay, that's defined. And in that case, neither one of these are used for figuring out significant digits. They're infinitely significant. It doesn't matter if it's 1,000 point as many zeros as you want to equals 1 point as many zeros as you want to. That's still going to be the same ratio. Going to be the same relationship. So that's defined. Since it's defined, we don't use these at all when figuring out significant digits. Okay? So we have 4 significant digits in our answer. We don't have to round that off at all. Okay? Does that make sense? So the key is to know when you've got a calculated or measured relationship for your equality statement, and to know when it's a defined relationship. If it's defined, it's absolutely infinite, or it's an absolute number. It's infinite. You know, the number of zeros you can put after the decimal place is infinite, and it's still going to be the same thing as far as that definition is concerned. And so we don't use those here. Okay, they don't really apply to figuring out significant digits. We only use the measured or calculated numbers, and these weren't measured or calculated. Okay, remember that? You only use measured or calculated numbers in figuring out the significant digits in your answer, and neither one of these were measured or calculated. Okay? All right. So then this is the number of digits we need in our final answer. You don't have to round off at all. No rounding off needed. All right? Are we good now? You want another practice problem? We're okay. You're good? Anybody else? Going once? Going twice? Huh? Do another one? Oh, okay. All right, do another one. I'm sorry, I didn't complete the 8. All right, so this problem says that there are 760.0 torr in 1 atmosphere. Now, these are pressure units. I know you don't know that yet, probably. Torr is named for a guy named Torricelli. Anyway, so if the pressure of a gas is 857.0 torr, what is that pressure in atmospheres? And ATM stands for atmospheres, okay? The ATM you may be familiar with is automatic teller machine. That's a capital A, capital T, capital M. This is lowercase a, T, and M, okay? Now, there's something different about this problem than all the problems I've given to you so far in these lessons. Can you tell me what's different about this problem? Yes?
3 numbers.
Okay. Is there 3 numbers? Okay, yeah. In the sense that there's no 1 you put under there. That's, I mean, yeah, you're right. I can give you just the 1, right? Okay, so there's 3 measured numbers here, okay, in some fashion. Yes? Or calculated numbers or whatever. All right, there's one other thing that's a little bit different. I didn't think about that one until you said it, but you're right. You know what?
The zeros after the decimal?
Well, I don't think that's so much different. We talked about them. What else is there different? There's no species here. Okay? That's okay. If there's no species, you don't use one. Okay? Species being some chemical name or some chemical symbol. Okay? There's no species here. That's okay. We're still doing dimensional analysis. All right? And by the way, the zeros thing, we'll shortly be talking about what zeros are significant. You need to know, just to help you right now, all the zeros in these problems are significant. Okay? Okay? So the 857.0 torr is what stands alone. We're going to put that over 1. 857.0 torr. Put that over 1. And so the other two things up here in this problem, and again, this is one I've kind of stated in a very simple way. You can tell pretty quickly what the equality statement is. It says that there are 760 torr in 1 atmosphere. That's our equality statement. 760.0 torr equals 1.00 atmospheres. And then we're going to put the side of this equality statement that matches the units in our starting amount on the bottom. We want to match units top and bottom. So 760.0 torr goes on the bottom, and 1.00 atmospheres goes on the top. We can cancel out torr, and we do the calculations. And I get, not a time sign, equal sign, 1.127631579, and that would be atmospheres. And I've got 4 significant digits in this problem, or in this number, 3 in this number, and 4 in this number. We want the number with the least digits of the measured and calculated numbers. Of all these numbers right here, this one's measured. These are actually calculated, but we don't worry about whether that's calculated or measured. They have decimal places. You can just assume they are. And so this has the least digits here, 3 digits. 1, 2, 3. Underline from here over. Draw an arrow to show that we're rounding off. And in this case, we're going to round up that 2 right there. So 1.13, that's 7 right there being 5 or greater, makes that 2 round up to a 3. 1.13 atmospheres. Huh? Which 0? Yeah, that matters. But there's only 3 significant digits in this number. So we want to match the final answer. Want to match the number of digits we keep in the final answer to the number of digits in the measured or calculated number with the least digits. Okay, so this one has the least digits. All right, everybody good with that? So this is homework.